What's up, guys? It's Mr. Brengle, and today we're going to be going over math for springs in terms of simple harmonic motion. So just to review over some things we've already talked about would be period and frequency and their reciprocals of one another. So to be specific here, this would be talking about the period or the frequency of the oscillation of the spring. Okay. Now, if you've done the spring notes, the spring discussion, then you've already been introduced to this next equation right here, F equals Kx. I'm going to make that a little bit bigger. F equals Kx. So this is what's known as Hooke's law. So you can see that right there, Hooke's law. And this is referring to the restoring force of the spring, okay? Restoring force. Okay, so remember, that's when you stretch a spring and you let it go, and there's a force that wants to move that object, the mass that's on the spring, whatever's on it, back towards the equilibrium position, meaning that if you have a spring that's, say, hanging like this, and it's attached to a mass right here, this line represents the equilibrium position where the mass sits, where nothing's touching it or pulling it or pushing on it. And then when you pull this down and it's now, say, stretched out like this, and it's down here, there's going to be a force in the spring that's going to pull that back up, right? So that's the restoring force. Now, K, you'll notice that they are using the term force constant, but this is what we refer to as the spring constant. Okay, it's just another term for it, but we will use spring constant in here. Okay, and that's measured in newtons per meter, so you can see the units right here, newtons per meter. And so what that really is a measurement of how much force is stored per meter in that spring. And a high K value is going to be a really stiff spring, so it's really hard to move, and when you do move it, it's going to snap back into place. And then a really low K value would be a very flexible spring, so something like a slinky that's really easy to manipulate. And then X right here, see, they refer to it as the displacement from equilibrium, also known as the stretch of the spring. So how far did we displace it from the equilibrium position? So that would be basically this distance right here. Sorry, I should have ended that right there. But this distance from here to here is what we refer to as X, the stretch or the equilibrium displacement from equilibrium. Also referred to as amplitude. Okay, so some of the stuff you've already been exposed to and we talked about in our other notes, but just to go back over it there, there's one other equation that we'll talk about here on the next page. So this is an equation very, very similar to what you already worked with in the pendulum math. So the period of a spring is equal to 2 pi times the square root of the object that's on the spring, its mass, over the spring constant. Okay, so this is mass, and this is spring constant. Okay, so since we've already used an equation just like that, we just want to be very careful about not mixing them up. When you're given a problem that could be a spring or a pendulum, we need to make sure if it's talking about length and acceleration due to gravity, we're using the pendulum equation, and if it's mass or spring constant, we're using the spring equation here. Okay, so let's go through 3 example problems here together, and then you'll work on some on your own. So the first one here says a hummingbird beats its wings up and down with a frequency of 80 hertz. What is the period? So this is nothing new. We've already done problems like this. Frequency is 80 hertz. We're looking for the period. We know that period and frequency are reciprocals. So period's equal to 1 over frequency, which will be 1 over 80 hertz. And this is going to be equal to 0.0125 seconds. Okay, so that's a really small time there, but that should make sense, right? Because we're talking about a hummingbird flapping its wings, which happens very, very rapidly. Okay, example number 2 here. In anticipation of her first game, Alicia pulls back the handle of a pinball machine a distance of 5 centimeters. Okay, so let's pause there and let's think about what that is. We're talking about a spring, right? So if you ever played pinball, you pull that handle back and there's a spring that basically brings it back to its equilibrium position, right? That restoring force is a spring. So this right here is the stretch, or the distance from the equilibrium point, x, and it's 5 centimeters. Let's go ahead and convert that into meters because we don't like to work with centimeters. We'll move the decimal place 2 to the left, divide by 100, and it's 0.05 meters. Okay. It says the force constant of the spring, or the spring constant, is 200 newtons per meter. So that's K, 200 newtons per meter. And then it says how much force must Alicia exert. So we're solving for the force. Okay, so we're going to use our equation that we just talked about, which is F equals Kx. We're solving for F. That's going to be equal to 200 newtons per meter times 0.05 meters. So you can see here that the meters are going to cancel and we're going to be left with just newtons, which is what force is measured in. And this is going to be equal to 10 newtons. Okay, looking at example 3 here. As Bianca stands on the bathroom scale, whose force constant or spring constant is 220 newtons per meter. So let's go ahead and write that down. The needle on the scale vibrates from side to side. A, if Bianca has a mass of 180 kilograms, what is the period of vibration of the needle as it comes to rest? So this is asking for the period of a spring. Okay. And then part B, if Bianca loses weight, how will this change the period of vibration? Okay, we'll come back to that. So first of all, if you don't know how your bathroom scale works, there are springs in the scale. And it basically is using this equation, F equals Kx, where the spring constant is a known value, right? So every spring has a different spring constant. So this would be a known value. And then it would be measuring the displacement of the spring, which then gives you a reading of a force, and newtons can be converted to pounds. So it's just a little computer doing a conversion there. So anyway, that's a side note. Our equation here, we're going to use the period of a spring is equal to 2 pi times the square root of mass over spring constant. I like to keep that 2 pi in parentheses for situations where we have to divide the period by 2 pi. Similar to or exactly like the period of a pendulum equation. And let's go ahead and plug this in here. So we're solving for period. It's equal to 2 pi times the square root of 180 kilograms over 220 newtons per meter. Okay, so we'll kind of do this step by step. Let's start by doing 180 divided by 220. Okay, so that's going to give us 2 pi times the square root of, that's going to be 0.81 repeating. Okay, so that's just 180 divided by 220. We leave that inside of the square root there. Now, we want to go ahead and square root that. Okay, so now it'll be period of pendulum is equal to 2 pi times, it should be 0.81 0.905 when you do the square root of 0.81 repeating. And then multiply that number by 2 pi, and your period of the spring is going to come out to 5.68 seconds. Okay, so that concludes the examples here. I want you guys to go ahead and try out the problem exercises, which will be 1 through 6, and then check out that video to check your work.